Hello everyone, I am Dr. Surpratap Gautam and today I am going to discuss the topic crystal structure. आज हम मेनली पढ़ेंगे लूज पैक्ड, लूजली पैक्ड और स्पेशल स्ट्रक्चर्स में डायमंड क्यूबिक। स्पेसिफिकली आज हम डिस्कस करेंगे सिंपल क्यूबिक स्ट्रक्चर बॉडी सेंटर्ड के प्रॉपर्टीज़ जैसे कि एटॉमिक पैकिंग फ्रैक्शन, coordination number and the relation between the radius of atoms and the two edge length. Okay, and we will get the formula for the relation of atomic radius and the cube edge length. Okay, so first of all we take the simple cubic lattice. Okay, so for this simple cubic lattice, as we know that the atoms are present on each corner of the lattice, and suppose the edge length of this cube is k. Okay. So actually this arrangement in real, if we take one phase, then the arrangement of the atoms are like this. Something. Okay, and this is his length. So we can easily understand that if the atomic radius is r, this is r, then the relation between atomic radius and the cube edge length a is a equals to 2r. Simply this is the relation with the atomic radius and cube edge length for simple cubic lattice. Now we will calculate the atomic packing fraction. For the atomic packing fraction, we know that the APF equals to the volume of atoms in unit cell upon volume of unit cell. That is, we know that the effective number of atoms in the simple cubic is 1 because each corner atom contributes 1 by 8 of its atom to the unit cell. That means the effective number of atoms equals to 1 by 8 into 8, that is 1. So the number of effective atoms is 1 and the volume of atom 4 upon 3 pi r cube, and the volume of unit cell, because this is cubic cell, so it is a cube. Now we get r, that is a by 2, 1 into 4 by 3 pi r, that is a by 2, that means a qy8 we can say, and we already have aq. So finally we get pi by 6. So this is the atomic packing fraction for simple cubic lattice, and it is equals to 0.52. That means 52%. Okay. Now we will also discuss here the coordination number for simple cubic lattice. So we can easily see that coordination number means the first near neighbor atom for any reference atoms in a unit cell. So if we take any reference atom in simple cubic lattice, suppose this is the reference atom, then for this atom how many nearest neighbor atoms contributed for the first nearest neighbor distance. So in simple cubic we can understand like this: one atom is coordinated with this unit cell which is present here. One unit cell is upper side and one unit cell is front side. So these are 6 atoms coordinated for first nearest neighbor distance, that is A, because the age length of this cube is A. So these are 6 atoms coordinated: first atom, second, third, fourth, 5 and 6. So there are 6 nearest neighbor atoms coordinated at distance A. So the coordination number for the simple cubic lattice is 6. Now we will discuss the body centered cubic lattice. So first we draw the body centered unit cell. In body centered unit cell, we know that the one atom is present in the body of the cell, unit cell. Complete atom is present here. So the effective number of atoms in the body centered cubic lattice is equals to 1 by 8 into 8 plus 1, that is 2. So the effective number of body centered lattice is 2, and now we will calculate. First we get the relation between the atomic radius and the cube age length A. So here we can say that the body diagonal, the length of the body diagonal is like this. That means that is equals to 4r. is the length of this body diagonal is equal to 4r equals to okay, under root 3a. So, okay, the length of this body diagonal is under root 3a, and this is also equals to 4r. Okay, now we get the relation simply r equals to under root 3 by 4a. So this is the relation between atomic radius and q wavelength. Now we calculate the atomic packing fraction. A, P, F. As we previously discussed that the atomic packing fraction formula is volume of atoms contributed by the atoms in unit cell and the ratio and the upon volume of unit cell, that is there will be effective number of atoms 2 and volume of atom by RQ upon AQ. So 2 into 4 by 3 5, here R equals to under root 3 by 4 under root 3 Q upon 4 Q into A. Simple. Okay. And upon A. So finally we get the okay, 2, 3, that is 2 into 5 3 root 2 upon 4. Okay, so we get here 3 root 3 5 upon 2, that is also equals to 0.68, or we can say 68%. So this is the atomic packing fraction for body centered, and now we see the coordination number, that is first nearest number atoms in body center. So this is the body center atom in body centered cubic cell, and for this all the corner atoms are nearest atoms here, and the distance is under root 2a by 2. So we can say here the coordination number for BCC equals to 8, because there are 8 corner atoms and presented at nearest distance with the body centered atom. Okay, and the distance at distance root 2a by 2, that is because it is body diagonal, so distance should be root 3a by 2. Okay, so now we will further discuss the coordination number and atomic pattern fraction for closely packed structures. These are face centered and hexagonal structures. For face centered, the atoms are presented on each face okay, this type. So the effective number of atoms in the face centered are 1 by 8 into 8 plus, because 6 atoms contributed half of the atoms, that means 6 into 1 by 2. So the effective number of atoms for BCC is 1 plus 3, that is 4. Okay, now we see the relation between the atomic radius and the cleavage length A. So that is, this is the phase diagonal. Phase diagonal is under root 2a, and this is also equals to 4r equals to 2a. So we get r equals to 2a by 4, that is under root 2a by 4. Okay, now we calculate the atomic pattern fraction equals to effective number of atoms 4 into 4 by 3 pi r, that is under root 2a upon 4 q upon volume of unit cell, that is 80. So we get 16 pi by 3 aq 2 root 2 aq upon 4 q. So that is equals to 4, that is 4, that will be 4, and we get 2 root 2 pi upon 3, that is 0.74 or equals to 74%. So atomic pattern fraction for the FCC is 74%. And now we see the coordination number for the FCC lattice. So for FCC it is FCC, the coordination number are, this is the, suppose this is the reference atom for FCC, and we have to calculate the nearest number of atoms. So we see here, if we draw one unit cell upper side, let's draw here. Okay, this type. This type. Okay, so For this reference atom, we get a 1, 2, 3, and 4. So the nearest neighbor distance is this. This is also equals to for these atoms, and these are the more 4 atoms which are nearest neighbor. The drawing may be uh, not good, but these are the nearest neighbor atoms for this reference atom in face centered cubic layers. And so we can say the coordination number or first near neighbor atoms for FCC is coordination number or first first nearest neighbor atoms for FCC are 12 at distance for FCC it is under root 2 a by 2. So we will discuss the special structures diamond cubic in next lecture, because this lecture is something large. So we stop the lecture here and we discuss the diamond cubic structure and some other special structures in next lecture. Thank you.